Hello everybody. In the last class we had started our discussion on induction machines or the induction motors. Induction motors are very popular. Something like 80% of the prime movers all over the world use induction motors for various applications. So it is important that we learn about the induction machine. So we began our discussion by an initial comparison of the induction motor with the three-phase transformers. In the case of three-phase transformers, we had the energy movement from the electrical side into the magnetic domain and then back again into the electrical domain in the secondary. In the case of the induction motor, it is also similar in the sense that you have a primary side coil called the stator, the secondary side coil called the rotor. Plus, there is also another domain called the mechanical domain. So, you have the energy which is moving from the electrical domain into the magnetic domain, and you can tap the energy in the electrical domain or in the mechanical domain or both, depending upon the type of the motor. So, in the induction motor, you have two main categories. The squirrel cage induction motor, where the rotor is shorted, you cannot take any electrical energy from the rotor. So, all the electrical energy can be taken only from the mechanical domain. So, you have the electrical domain, magnetic, mechanical domain as the path for the energy. And the case of the other category, the wound rotor induction motor or the slip ring induction motor, you have the electrical domain energy enters the machine, goes into the mechanical domain, and the energy can be tapped out either in the electrical domain of the rotor or the mechanical domain of the rotor. And all the working principles and operating principles of the transformers are valid even in the case of the induction motor. You have the Faraday's law of electromagnetics, E is equal to BLV, which induces the voltage on the rotor conductors and thereby a current in the rotor conductors by virtue of the relative motion of the rotor conductors with respect to the field inside the machine. And because there is a current in the rotor conductors and there is a field in the machine, by virtue of the Lorentz law, that is force is equal to BIL, there is a force which is induced on the rotor conductors, and the accumulated force on all the rotor conductors creates a torque and which makes the rotor move. So this is how we get the mechanical motion. We will look into the details of that much later. But the important concept now is that how do we bring about a relative motion between the field in the motor and the rotor conductors. Now, to achieve that, we use the three-phase source. So, in the three-phase source, we have three sources wherein they have the same effective amplitudes, however, they are 120 degrees apart in time. Now, applying one more constraint, that is the currents from these three sources flow through coils in the stator of the motor, wherein the coils are physically located in space 120 degrees apart. A combination of these two produces a rotating magnetic field. So, let us now see how this is created. First, we shall have the rotor represented as a nice circle here, and let me have the circle is not as nice, but let us improve the circle, and let us have the three-phase currents flow through three poles, electromagnetic poles, located 120 degrees spatially apart. So, let us say the A phase current flows through a phase, this is, let us say, flows through a phase pole set, and let me indicate the pole, the salient pole in this manner. So, you have one pole pair, per phase as shown here. Then let us have 120 degrees apart one more set of poles which are like this along this axis as shown. Now this is 120 degrees apart, 120 degrees. Now along this also I am going to have some fixed stationary poles. Pole pairs, of course, you can't have single poles. You should always have a south and a north pole. Now one more pole set which is placed 240 degrees with respect to the A axis, and this is 240 degrees with respect to A axis, 240 degrees. This is the C axis, and of course the red one is the B. So on the C axis also we are going to place the stationary poles as shown here. In this manner, you see. Now we can of course connect all these into the same structure, and that structure is called the stator. So all these are connected into the same structure, and that structure is called the stator. So we have the stator like this as shown, with salient poles projected inward, and we have the rotor in blue. Now let us say we have the three phases, and let me take the A phase, and the A phase you have a coil as shown here on the stator, and internally the same current whatever is entering here, let me call this one as IA from the A phase source. Internally this coil is then brought in and connected, wound around the other part of the pole to get the south pole, and taken out. And then we have the B phase. So I am going to take the B phase part, wind it around the pole here, then bring it to the other side, and then take out this direction. So we have IB which will flow here, and then IC. So we will take IC which is going to flow like that, taken all through like this, and goes out. Now the other ends are joined together. So let me join this end, this end, and this end, and that is called the neutral. So the other ends of the coils are joined together, that is the neutral. So you have the other open end through which the source is connected, and you have the IA, IB, IC flowing. So IA is flowing through the A phase pole, this is stationary, fixed, and IB is flowing through the B phase pole, that is also stationary and fixed in space, 120 degrees shifted with respect to the A phase pole, and IC is flowing through the C phase pole and the C phase axis, and that is also shifted 240 degrees with respect to the A phase, this one, in this manner. So this is a star connected induction motor. The stator coils are star connected with the currents IA, IB, IC flowing in this manner. So we have the three phase currents, 120 degrees electrical in time, that is when this is at 0, this is negative, this is also negative, like in a three phase current. So the amplitudes here along these three axes vary according to the time. Let us see what happens to the amplitudes of the flux. So as the current flows here, we have a phase flux in this direction, we have a B phase flux in this direction, and we have a C phase flux in this direction, with the amplitudes changing according to the instants of time. So now let us see if we apply a three phase sinusoidal waveform, how does it look? So we generate a three phase sinusoidal waveform by the method that we followed before. Just draw this triangular wave shape, then connect the tops with curves like this as shown, connect the bottoms of the vertices with curved lines like this, and you have your three phase wave shape with respect to time. Now let me have the axis, the vertical axis at this point, the 0 point here. So blue is the A phase, and let me call that as IA. 120 degrees phase shifted would be our B phase, and I will call that as, I will use the red color for that. So that is our B phase current IB effective value, and then the C phase current is given by the violet. So it comes in this fashion, which is 240. You see that it is now cutting the 0 and going positive 240 degrees with respect to the A phase. So these are the three phases I, C. Now we will look at some crucial critical points. Okay. So let us have point of interest is, let us say, some of these points could be points of interest. Now I could also take a point along this. Now let us take these. and this is also another point of interest, and we have and let us and so on. Okay, every 60 degrees. Now let us say when I take a section at that point, how does the resultant vector look like? Now there is going to be a flux along the A phase axis at every instant of time, B phase axis, C phase axis. Now if we take at that point of time, at this point of time, so we have A phase current is maximum positive direction, so I will put it as A phase is maximum positive direction, B phase is half negative, so this was B phase, so B phase negative and half, C phase is also negative and half, C phase negative is this direction and half. So you have a resultant which is having, let me draw a circle. So the resultant is having a direction in this, that is these two add up and then you have a resultant in this direction. Now if we consider this point now, let us say, or let us take this point here. Now here you have B as maximum, so B as maximum positive, so I will put it as maximum positive here like that. A is negative half, A is negative half, and you also have C which is negative half and C negative half. You see that the axis directions are always the same, that is the mechanical axis directions are always the same, only that positive and negative. So which means now the resultant is, the resultant flux is now shifted, and it is shifted like that. And then if we take a point here, now you will see that IC is maximum positive, so you have maximum positive here. IA is negative half, IA is negative half, IB is negative half, and that is negative. So therefore you will have a flux which is in this direction. So you see that the resultant flux, as time progresses, it was in this direction, then it has rotated in that direction, rotate. So we have taken some crucial points in between to show that the flux positions are changing. So if we smoothly go along the time, you will see that there will be a smooth rotation along this circle, and then you will see that the rotating magnetic field has been created. So this vector which we are seeing here is rotating smoothly around the circle, and that is the rotating magnetic field. So once we have the rotating magnetic field, which is rotating inside the machine in a circular fashion, so the magnetic field here is in space, it keeps rotating. If we apply 120 degrees electrical phase shifted sine waves to the three coils which are also 120 degrees phase shifted in the mechanical, that is in the stationary spatial coordinates. Now as this is rotating, and if we have a rotor conductor, this magnetic field which is rotating is cutting this rotor conductor, and as this is cutting the rotor conductor, there is a current which is going to flow through the rotor conductor, and that is I. There is a length of the conductor L. This magnetic field is of intensity B. So by the Lorentz law, you have a force which is BIL that gets produced, which will push the conductor in an orthogonal fashion, that is the direction in which the current is flowing and the direction of the field in this case, and then you will see the third finger will give you the middle finger will give you the direction of the force. So this will cause the conductors to move, and it will try to catch up with the field which is already rotating. Initially, when the rotors are not moving, the field is rotating at whatever the applied frequency, and there is a very large relative speed between the rotating magnetic field and the stationary rotor conductors, and therefore that is going to induce a very large current in the rotors, and which is going to give you a huge torque. And then the rotor starts rotating and tries to catch up with the magnetic field, and the relative speed starts decreasing. So as the relative speed starts decreasing, the induced current in the rotor also starts decreasing, thereby reducing the torque to a steady state value. Now suppose, let us say that the rotor has caught up with the magnetic field, which means the magnetic field and the rotor conductors are rotating at the same speed. This means there is no relative speed between the magnetic field and the rotor conductors, and therefore there is no cutting effect of the magnetic field, and therefore there is no induction of the current in the rotor, and as a consequence there is no current in the rotor, and therefore there is no force for the rotors to move, and therefore it will again lag behind. So the rotors will never catch up. There will always be a slight difference between the magnetic field rotation speed and the speed at which the rotor conductors rotate, and this difference is called the slip. This difference in speed is called the slip. So if the magnetic field is rotating at a speed, let us call ns, called the synchronous speed, in RPM, and the rotor conductors are rotating speed nm. This is the mechanical speed of the rotor, mechanical speed of the rotor in RPM, then slip S is given by ns minus nm by ns, and it is a value which ranges from 0 to 1. Yes, we shall come back to the concept of the slip a bit later again. We shall revisit that, but now we should try to understand what happens if we put more number of poles. We saw in the picture here that there is one pole set, there is one pole pair per phase. Now for every phase you could have more than one pole pair. In such a case, what happens to the speed? What happens to the synchronous speed? So let me just explain the concept with respect to just one phase, that is the A phase. What happens? So let us say we have the rotor here, and we have one set of fields, and that is, let us say, the A field. So let us explain with respect to just this A field. So we have the A field like that with coils wound and all those things. Now imagine that inside in the rotor, imagine there is a imaginary dumbbell okay. So one is the north pole and then others the south pole. So as the coils here are fixed, the pole here is fixed, this dumbbell does not rotate, it only shrinks and expands. Let me first make a copy of this because I will be using this later. Copy. Now let us see what happens to this dumbbell as time progresses, and we have a sine wave which is applied to the coils. So let's say this is IA and this is applied to the coils here, and then we have also the coils like that. This is connected to the neutral and this is connected to this, and you are passing IA through that. Okay. So at this point IA is 0, the flux intensity at that instant is going to be 0 because Ni is going to be 0 at that instant. So the MMF which is at this instant is also going to be 0. So the MMF is going to follow more or less this curve because it is Ni. So what happens to the dumbbell inside? So the dumbbell inside, which represents the magnitude of the flux, will be residing here. There is no amplitude because it is 0. Now as the amplitude starts rising, so let us say at some point here, the corresponding flux here would be somewhere, would result in a dumbbell which is of this size, north and south. And then at some point here, the peak amplitude, the dumbbell would have lengthened and you will have the maximum peak amplitude of the dumbbell like that. And as it starts coming down, the dumbbell shrinks and then at this point again comes to 0. At this point it would again come to 0 and then further when the current starts going negative, what happens is now the dumbbell reverses polarity. That is, you will have a dumbbell which is half the size. Now this is south and this is north. note the change in polarity, and then a corresponding value negative peak, it would reach the negative maximum. So what would happen is that you would have a dumbbell which would reach the negative maximum, that is, this is south pole and north pole. So like that, you will see the dumbbell which is swinging along that axis depending upon the amplitude of the current. Now let us take just the two crucial points, that is this point, this and this point, that is the positive max and the negative max. So at these 2 points we will see that the dumbbell size or the length will be the same maximum, except that during the positive max it is going to be north on this side, south on this side, and during the negative max the dumbbell length is going to be the same, except that it is going to be south on this side and north on this side. That is, in a half cycle, the dumbbell has rotated and shifted by 180 degrees. So inside, if we take the imaginary dumbbell which is on the rotor rotating, it means that the flux MMF inside has rotated 180 degrees for a half cycle traversal of IA, and it would have rotated full 360 degrees for a complete full cycle traversal or 2 half cycle traversal of A. That is for a 2 pole system. That is, this is 2 pole, pole 1, pole 2. So you have a 2 pole per phase. So you have 2 poles per phase system. Now in this 2 pole per phase system, 360 degrees is traversed by the dumbbell, by the MMF dumbbell in 2 half cycles of the IA or the current wave. So now let us say the current wave has a frequency f. That is, this current wave here has a time period of t and the frequency f is equal to 1 by t. So in our case f is equal to 50 hertz because it's a 50 hertz mains in our country. So f is the frequency of the sine wave. So it makes full 360 degrees, dumbbell makes full 360 degrees, or let us say 1 revolution in t seconds, or 1 by f seconds. So in 60 seconds, for a minute, in 60 seconds, that is 1 minute, how many revolutions does it make? So it is 60 by 1 by f, or we should say 60 f is the revolutions per minute, and this is your ns. Okay, this is your ns. This is for 1 pole pair. one pole pair per phase, or should we say there are two poles per phase. So if we use this notation, that is, instead of saying pole pair rather than poles, then we say it is 60F by pole pair. If it is two poles, then let us say P is the number of poles per phase. Then NS will be 60 into F, let us say, into 2 by 2. This should be for two poles, so that you still have the same result. This will be 120 F by 2, where 2 indicates number of poles. And in general, if there are P number of poles, NS is equal to 120 F by P, where P is the number of poles per phase. What does it say? As the number of poles, this is always an even number because you cannot have single poles. This means that as the frequency increases, the synchronous frequency increases. As the number of poles increases, the synchronous frequency decreases. Let us see how this happens. Now, of course, I will explain it again only with respect to the A phase. Let me have this figure. So here we have just one pole pair or two poles. Here P is equal to 2. Now let me have two more poles in the A phase, all A phase, and the windings are so done such that the north and south poles alternate. All the currents flowing through this, and then this, and then this, and then this, they are all IA, 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 and IA is flowing through all these four. And then there are 4 sets of other B phase which are tilted and shifted 120, that is 120 degrees axis, and then another 4 sets for the C phase. So they are shifted and placed in such a manner, meaning, just to indicate, so we have, let us say, the rotor. So let me say this is the A pole set, that is the A phase, and the B phase, let us say, is shifted 120 degrees. You have one here, like that, and like that, and the C pole set is again shifted 120 degrees, will be in this manner. Only it is minus 120 degrees. The winding sense is changed from clockwise to anti-clockwise to obtain the 3 phases. So anyway, let me explain it with respect to only one phase to give you the idea of how the synchronous frequency changes with the number of poles. Now we have 4 poles. So at any given point of time, we will be having 2 dumbbells, imaginary dumbbells, which are like that. So we have these 2 imaginary dumbbells, and let us say this is north, this is south, this is south. So north, south, it alternates throughout the whole circumference. Now let us have the IA current also. This is IA current at this point. Let me copy this whole portion, copy, and let me also paste it and have a duplicate here. Let me shift this above, make some space so that you will be able to include this here. So now let us see what happens at these two critical points. That is, one point is the positive max and the negative max. So what is happening? Now let us say at this point, okay, IA is positive max. Let us say this is the position, IA is positive max. Now you have IA is negative max. So between the positive max and the negative max, there should be a 180 degree, that is, the north and south pole should interchange. So here we have the north, north, south, south. So that is at the positive max. At the negative max, north and south pole should interchange. So we shall interchange the north and the south poles. Here. See the north and the south. So south becomes this and this becomes north. So which means there is a movement of between this and this. It looks as though the MMF has rotated by 90 degrees. Between this and this, the MMF has rotated by 90 degrees mechanical. But however, here you have one complete half cycle, T by 2. That is one half cycle. So one half cycle makes the MMF rotate by 90 degrees, and to get 360 degrees you need 4 half cycles or 2 cycles to complete one complete revolution of this one. So which means if there are two pole pairs, that is N, S we saw was 60 F. If there are two pole pairs, that is, if there is one pole pair, it is just 60 F by 1. If there are two pole pairs, it has become, one has become 2 cycles of this one is needed to make one complete mechanical revolution. So the mechanical speed, the mechanical synchronous speed is 60 F by 2. And if there are 3 pole pairs, it becomes 60 F by 3. Now if you want to express it in terms of number of poles rather than pole pairs, then you have to multiply this and this by 2, which means you are talking of 120 F by 2 poles in the earlier case, and then in the case of this 4 pole machine, you have Ns is equal to 120 F by 4 poles per phase, and so on. So if you have P poles, it becomes 120 F by P poles. So you see that it actually slows down the system if you have more number of poles. So the ns, the synchronous speed of the flux, is 120 F by P. Here P is number of poles per phase. So be careful about this. Now here, if you can also have 60 F by PP, where PP is number of pole pairs per phase, because these are various formulas that you will find in different literature. It is better you know the nomenclature. And PP is always P by 2, number of poles by 2. And NS, this is in RPM. This is in RPM. Now the synchronous speed is also expressed in radians per second, because radians per second is the SI system of units, so you should know how it is converted. So in the SI system, if you say synchronous speed is given as omega s, is the synchronous speed. Synchronous speed in radian per second. So to convert something to radians per second, that is 60, let us use 60 F by PP. This is in RPM, and we want to convert into radians per second, becomes 2 pi by 60. So this we saw while doing the DC machines, conversion from RPM to radians per second. You multiply it by a factor of 2 pi by 60, and therefore you have 2 pi F by PP. And this is the applied frequency. So omega synchronous is equal to omega applied by PP. Or if you want to express it in terms of this one, it is 2 omega applied by the number of poles. So this is also something that you should know, how to express it in radian terms. Now let us just have a small example from the book. Let us say we have a 3-phase induction motor, 3-phase induction motor, which has 20 poles per phase, and it is operated from a 50 Hertz 3-phase source. Now what is the synchronous speed? Synchronous speed. So we know that ns in RPM is given by 120 applied frequency by P, where P is the number of poles per phase. So this will be 120 into 50 divided by 20. So that is 300 RPM, revolutions per minute. Now we have also defined the slip. The slip, which is S, is given by ns minus nm, that is the rotor speed, mechanical speed, by ns. And this is something always less than 1, because ns is always greater than nm. It could also be written as omega s in radians per second, omega m in radians per second, divided by omega s, where this is in rpm and this is in radians per second. So this is the slip. Let us take a simple exercise on this from the book. So we have a 6-pole induction motor, and this is excited by a 3-phase 60 Hz source. The full load RPM is 1140 revolutions per minute. Calculate the slip. So first let us say what is ns. Ns is 120 F by P, which is given by 120 into 60 divided by 6 poles, which is equal to 1200 RPM. 1200 RPM. Now slip S equals 1200 minus the full load motor RPM divided by 1200, and this is equal to 60 by 1200. And in terms of percentage, which is equal to 0.05, and this is something like 5% in terms of percentage. So this is how one calculates the slip. Now there is one important thing that you should know. We saw that there are machines with different number of poles. You have the 2-pole machine, the 4-pole machine, 6-pole machine, 8-pole machine, 20-pole machine, so on, for different applications. What is the maximum speed that one can achieve, that is maximum synchronous speed that one can achieve for a given frequency source, and that is at 2 poles. That is, if we have just 2 poles per phase, that is the maximum frequency that you could get, which means ns is equal to 120 F by 2, or which is 60 F, is the maximum synchronous NOUS frequency for a machine that is operated or excited from a F Hertz source. So in India, F is 50 Hertz. So therefore the maximum synchronous speed can be 60 into 50, which is equal to 3000 RPM. And many of the machines which are there in the market are 4-pole machines. 4-pole machines, which means the NS typically of all these 4-pole machines in our country, you will see they are 1500 RPM. which will be on the nameplate. So keep that in mind. Now there is one thing that I have to show you, and that is a picture, an exploded view picture of a induction motor taken from one of the textbooks that I have referred and I have also introduced during the introduction class. So let us see this picture. So you see that this is a picture of an induction motor that is broken apart, that is split apart. This is called the exploded view of the induction motor. Now look at the various parts. Now let me move the cursor here on this part. This is the rotor. This is the shaft and this is the rotor, and the rotor is die cast. It's aluminum die cast, and it is shorted at both the ends. You see this aluminum ring here shorts all the coils. So all the coils are shorted, and that's why it looks like they say it's a squirrel cage. So this is a rotor, and then inside here you see some coils or windings, and that is the stator windings which form the various poles, the A phase poles, the B phase poles, C phase poles, so on, which are wound on the circumference of this stationary system, and that is called the stator. So this whole coil is wound on the stationary system, this yoke, this is called the yoke, and that is the stator, that is anchored onto the ground through these foot plates, and that doesn't move. So that is why we say that once the poles are fixed in space, they are fixed in space, they don't rotate. And what makes the flux to rotate is basically the by virtue of the three-phase source that you supply, which are 120 degrees apart. And this rotor is inserted into it, and then you have the end facing plates. These are the end plates here. This is one end plate and this is one end plate that is fitted in through these bolts, and then there is bearing, which you see also the bearing here which fits into this thing, and that will cause a smooth rotation of the shaft here. And here you could also see beyond this face plate there is something mounted on the shaft, and that is a fan, and beyond that there is another enclosure, a covering for the fan. So this fan is to provide cooling for the machine, that is, this is a air cooled enclosed air cooled induction machine. So this is how the various parts of the induction motor would look like. This is a squirrel cage induction motor. Now all these windings here are brought out. There are three, so all these windings are clubbed together and brought out as three terminal points here, A phase, B phase, C phase, and also the neutral. You saw that we connected all the neutrals together for the other end of the coils of the various phases. The neutral and the A, B and C phases are brought out as terminal inside this box here, through which the connection to the external source is done. Okay. So this is how an induction motor, a typical induction motor would look like for a given rating. Of course, for various ratings the sizes will be different. So this is all for now for this particular class. We shall continue in the next class with more details on the slip, the formulas, the torque speed characteristics, and the equivalent circuits, so on and so forth. Thank you for now.